Hey everyone, today we're going to take a look at some quantitative problem solving with inclined planes. So to start here, I have a mass on an inclined plane, and that inclined plane is being raised from the horizontal. And once it gets raised up to this 22 degree angle here, we notice that the box just starts to slide at this angle. So if we think about that, what does that really mean in terms of forces? Well, if I consider the system to be the block here, or the box here, I know that I have a weight force equal to 7.5 newtons. I know that my normal force will be perpendicular to where these two surfaces meet, so my normal force is somewhere up here. I know that because this thing is not moving yet, in order to get this box to start sliding, the maximum static friction force has to be matched. So when I think about this problem and I know that the box just starts sliding at this angle, this means to me that whatever I find the x component of mg to be, that it'll be just equal to the static friction force. So what I'm doing right now is I am sketching in my y-axis and my x-axis, and I'm just going to repeat that x and y-axis underneath here. Okay, and I'm going to put my normal force and my friction force in my force diagram because those are right on the axes, so those are dealt with. Now, like I said before, if the box just starts sliding at that angle, then I know that acceleration in the x is going to be 0 meters per second squared, and the F net in the x direction will also be 0 newtons. When I think about a box sliding down an incline, I know that the acceleration in the y direction is also 0 meters per second squared, and the F net in the y direction will also be 0 newtons. So because of that, I know that whatever my y component of mg is, it will be the same magnitude as the normal force. And this can be found, this y component of mg, as mg times the cosine of the angle of the incline. And so it'll be mg times the sine of the angle of the incline. Okay, so what I want to do now is let's figure out what mg sine theta and what mg cosine theta really are. So I know that I can find both of these. I can find mg sine of theta because that would simply be 7.5 newtons times the sine of 22 degrees. And I can also find mg cosine theta. This would be 7.5 newtons times the cosine of 22 degrees. So I'm going to throw these in my calculator and see what we get. Okay, so for my x component here, I got about 2.8 newtons. So I'm just going to add that in here. And then for my y component, I end up getting 7 newtons. And I'm going to take a look at the grid that I made here, my y-axis. I'm going to make up positive and down negative. And for my x-axis, I'm going to do to the right positive and to the left negative. So therefore, this 2.8 newtons will be a positive 2.8. And the 7 newtons I found for my y component is going to be a negative 7 newtons. Okay, so now I'm going to go over to my Newton's second law work up here and take a look at my net force statement in the y direction. So basically what I'm saying is that my mg cosine theta plus the normal force will equal 0. Now that I know that mg cosine theta is negative 7 newtons, I can also find that the normal force here is equal to 7 newtons. All right. Next thing we can find is we can think about what is going on in the x direction. So I can sum up the forces in the x direction. I'd be summing up mg sine theta plus the frictional force. And I was able to find mg sine theta to be 2.8 newtons. So this means that if I subtract 2.8 newtons from both sides, I would find that my frictional force is negative 2.8 newtons. Another quantity I can find is I could probably find the coefficient of static friction, the maximum coefficient of static friction here by using my friction math model and solving for this coefficient. So I know that this is 2.8. I know that my normal is 7 newtons. So that if I want to find the coefficient, I need to just divide both sides by 7 newtons. And if I do that, I find that the coefficient would be 2.8 divided by 7, which is 0.4. All right, ready for another example. In this example, we have an inclined plane, and we have a man here pushing this crate up the inclined plane. And it says that he's moving at a constant velocity of 0.3 meters per second. The coefficient of kinetic friction is given, and we know the mass of the box. So the first thing I'm going to do is I'm going to draw in my v vector. Okay, so this is a constant velocity of 0.3 meters per second up the ramp here. And if I know that there's a constant velocity up the ramp, I know that acceleration is 0. All right, now the first thing I'm going to do is draw in my force diagram. So I know I have my weight force, and I can quantify the weight force because I have the mass. So my weight force is going to be 300 newtons towards the center of Earth. I've got the normal force. If the v is this way, then my frictional force must be opposite the velocity. So my frictional force must be this way. Okay, if I think about what my x and y axis would look like, I'm going to have my y axis along the normal, and I'd like to do the friction force here along the incline. So there's my x-axis. Now what I'm going to do is I'm going to add the applied force of the man on the crate. So this would be right here. I don't really know how long to make that vector, but I'm just going to call it man on the crate. Okay, and again, our system here is just simply the crate. So now when I come down, I've just repeated my x and y axis here. Normal is on the y axis, so I'm going to sketch that in. My frictional force is on the x axis, so I can sketch that in. The force of the man on the crate, hold on, it's a little bit messy for you. The force of the man on the crate is here. I don't really know how long to make that just yet. And now I have to think about resolving this mg. Okay, so I want the y component of mg. What I know about what's going on in the y direction is I know that acceleration in the y direction will be 0 meters per second squared, because I know that if he's pushing the box up the crate, then there's no acceleration in the y direction. So this means that I know that I also have a net force in the y direction of 0 newtons. So let me draw in here my y component of mg. My y component of mg is going to be mg cosine theta, where theta is the angle of the incline. Now, when I think about the x component of mg, sometimes what I like to do is I go into my original force diagram, and around mg, I like to draw a rectangle, and this is just to kind of help me visualize where the components of mg will be. So when I look at the line from my rectangle that ends up on the y-axis, that becomes my y component, which you can see I put right here. And then if I look at what lines up on the x-axis, that would be where my x component is. Now, just kind of looking at this diagram here and knowing that it's a constant velocity motion, if I make the force of the man on the crate that magnitude, I know that the frictional force is going to be a little bit smaller than how I initially drew it. So I know that my frictional force is still there. It's just going to be smaller because I'm going to need my mg sine of theta, my x component of mg, plus friction to equal this force of man on the crate. So because it says constant velocity here, I know that not only is a in the y 0, but a in the x is also 0, and this means that net force in the x direction is 0 newtons. Okay, so let's take a minute here to see if we can find mg sine theta and mg cosine theta. Okay, so working out the math on this here, you find that mg sine of theta is 150 newtons. So I'd like to just write that in right here. And I'm going to make that a negative 150 newtons because using this as my y and this is my x-axis, I'm going to make that side positive, negative, and this negative and positive. So this will be a negative 150. And then my 260 newtons for my mg cosine theta is also going to be a negative 260 newtons. Okay. So if I take a look at what's going on in my x-axis here and what's going on in my y-axis here, I'm now set up to apply what I know about Newton's second law. So let me take a look at what's going on in the y. Net force in the y we said was 0 newtons, so therefore we can write a math statement for our net force in the y. Net force in the y is equal to mg cosine theta plus the normal force. So this means that we've already found mg cosine theta to be negative 260 newtons. And this means that if we add 260 newtons to both sides, we find our normal force to be 260 newtons. Now we have our normal force, and we know the coefficient of kinetic friction. So this allows us to find our frictional force. Right? So the math model for friction is F normal times the coefficient of friction, and we have our F normal is 260 newtons, and our coefficient of friction is 0.35. So we can calculate our frictional force, 260 times 0.35, and it's about 91 newtons. In the picture here, I have the frictional force going to the left, which is the negative direction for me, so I'm going to have this as a negative 91 newtons. Okay, cool. Now that we know what our frictional force is, we can take care of these forces in the x direction. So if net force in the x direction is 0 newtons, I can write a math statement for this. This would equal mg sine theta plus friction plus force of the man on the crate. So we end up with mg sine theta, we end up with negative 150 newtons plus negative 91 newtons, and we're looking for the force of the man on the crate. Okay, so we end up with our 91 and 150 being summed together. That gives you a negative 241 newtons plus force of man on the crate. So we find force of man on the crate to be 241 newtons. Thanks for checking out the video, and I hope you have a great day.